Welcome to this short introductory web lecture on stochastic and time-dependent parameters. Throughout this web lecture, we're going to use the example of a bike sharing system, and in particular the TOE bike sharing system. TOE bike sharing system needs to ensure that sufficient bikes are available in all buildings, which means that they need to move these bikes between the different locations to ensure that they meet the demand. And the problem now is that demand as a parameter clearly fluctuates over time. So here in this picture, for example, you see that demand changes. So we have a morning peak, we have an evening peak, but we have a little bit less demand in between. We also have some seasonality over the year. We have some differentiation throughout a comparable week. So for example, Wednesday usually sees completely different demand than a Saturday. And this is what we refer to as time-dependent demand. And a time-dependent demand means that demand changes between different time intervals within the same planning horizon. A time-dependent demand usually has an exogenous reason. So in the case of demand, in case of time-dependent demand in a bike-sharing system, this could, for example, be just the underlying need to go to work, to go to university, etc., which of course steers how our demand looks like. And time-dependent demand oftentimes requires explicit consideration in our planning models, which means we need to include these time dimensions. And that is the case if those fluctuations grow too large. So if, like in this picture that we just saw here, the peaks are extremely different from the low points, then we definitely have to consider this. So another case that we're having is travel times. Travel times is also a parameter in our model because, of course, if people all of a sudden start borrowing bikes for 2 hours instead of 1 hour, this also influences how many bikes we expect to have at the destination location. So we also need to consider this, and this is also, for an example bike sharing system, the travel time distribution. So this is how long people measure that the same origin destination pair, otherwise comparable, takes. And this clearly differs. This can, for example, be that one person is just a little bit slower when biking, while another person takes a break somewhere in between. But in general, we need to consider that these things are different. And this is what we refer to as stochastic parameter, or in this case, stochastic travel times. And stochastic travel times is a parameter that changes randomly between two comparable instances, between two comparable trips in our case, and may require explicit treatment. Also here, if it changes significantly, if those changes affect the way that we make our decisions, then we should consider it. And if we're talking about mathematical modeling, there's two general ways to attack this. One is to look into different scenarios, and another one is to look into distributions. During this web lecture, we won't go into more detail on how to do this. At this point, it is sufficient to know that there is methods to include this. But of course, if you're interested in that further, there's a lot of very good books that tackle stochastic parameters and how to include them in stochastic programming, for example. What I would like to know from you is if travel times can also be time-dependent. So we saw so far stochastic travel times and we saw time-dependent demand. And I would like you to think about when travel times can be time-dependent or if travel times can be time-dependent. One case we're now going to look into is actually the exact opposite. So we're going to look into a case where we have stochastic and time-dependent, but we're looking into demand. So we're having a bike sharing system like this one. This is our underlying demand. So we have 6 people that might potentially choose this system. And we're just, for the time being, assuming that every one of them chooses this system with a 50% probability, which gives us a distribution of how many people we actually anticipate, which of course means that the actual demand might be these 3 people, it might be these 3 people, or these 3 people. On all of these cases, we have exactly 3. But that is, of course, not always true. It is very possible that we have 0 or 6 people as well. And I would say it's rather common to have 2 or 4 in this system. And this is what we now see in this second time step, we still have an underlying demand of 6, but here we see 3, here we see a realization of 2, and here we see a realization of 2 as well, even though in all cases the expected value would be 3. So this case so far is just stochastic but not yet time-dependent demand. And now let's look into how this might look like if we have stochastic and time-dependent demand. So in this very simple example, we just have an underlying demand and all of them appear with a 50% probability. We have this base case where we have these 6 bicyclists and all of them appear with a probability of 0.5. But then in a second time step, we have actually an underlying demand of 8, out of which actually 4 appear. And in a third time step, we have an underlying demand of 4, of which actually all 4 just randomly happen to appear. So here it looks like the demand is the same, but actually the underlying demand distribution is not even nearly the same. And now let's look at a second time step. So now a different realization of this same demand could be 2, 2, and 2, and the underlying distribution still remains an expected value of 3, an expected value of 4, and an expected value of 2. But we see that the actual realizations is considerably different. And of course, if this is a bike sharing system, then it might matter very much for us how many people actually show up. What I would like you to take away from this web lecture is, first of all, what time-dependent demand is. Secondly, what stochastic travel times are. And lastly, I would like you to look into time-dependent travel times. Is it possible that travel times are also time-dependent? Thank you very much.